So मैं पाकिस्तान कब साल हो तो हाँ एक्चुअली कराची और समर कॉलेज मैंने कोई 12 साल तो वहाँ कुछ चलाया उसको अच्छा नहीं अच्छा I think I still होगा नहीं 1 घंटा भी नहीं खास कर लाइन में तो आप वहीं लाहौर तो यहाँ से कनेक्शन आपको बड़ा खुशी हुई हम लोग पहले ढाका में फिर हम कराची गए एक्चुअली मैं दोनों उर्दू बोलना तो एक ज़माने में आइडियल सिचुएशन थी उसके बाद चीज़ें बहुत बदल गई So Kamru, should we wait another few minutes? Wait a few minutes. Should we wait a few more minutes?
Central Florida, and the title of the talk is Novel Low-Dimensional Materials for a Sustainable Future.
Okay, thank you very much. First of all, many thanks to the organizers for inviting me. When I heard, I accepted right away, even though I was already supposed to be at another meeting. And the reason for that is that I grew up in Dhaka, and then went to Pakistan, and then of course I've been in the U.S. for a long time. And so all these places here, including Bose's name, Curzon Hall, all of those things are very much part of my growing up. And so I said, of course, I will definitely come to that. And so there's been lots of flashbacks, and in fact, well, before I do that, I had this slide but the students are not here, so I'm going to skip it. But I did mention here that it would be nice to get together with all of you who are interested in looking at prospects for physics, prospects for what you can do, opportunities abroad, opportunities here, and we will find some time when we can talk about these things. I'm from University of Central Florida, as you heard. So what I'm going to do today is talk a little bit, I had to decide on a topic, something that was related to Bose, and I'll talk about the excitons. And also I didn't want to really get into this thing about Nobel Prize because I don't think the quality of physics that you do or the impact that you have in the world or in physics or in science isn't really dependent on whether you get a Nobel Prize or not. In fact, I didn't even know that he didn't get a Nobel Prize, but he half the world is boson, right? So you're either a fermion or a boson. So that's the most important part. So I'll talk about excitons and about 2D materials because that is something that, of course, is very popular because of the prospects that it offers. And then I'll do a little bit about chemistry and tell you how a physicist can be doing things, answering some questions in areas where traditionally chemists have been dominating. And then if I have time, I'll talk a little bit about what could be done to broaden the participation of physicists from developing countries, and also how to enhance the quality of knowledge, the quality of your preparation as a student, as a scientist. So there's some efforts in that regard. So let me see how much I can cover. But before anything, I was just looking, and in fact, just about half an hour before this talk, there was a flashback that my very first paper was actually on triplet exciton fusion. And that was just about the time that Bose-Einstein condensation of excitons was being talked about. Of course, since then, I've moved quite a bit away from that area. However, excitons became quite important with the discovery of 2D materials. Of course, as you all know, 2D materials, it began with graphene, and after graphene, they have now a whole range of materials. These are the so-called van der Waals materials, and the reason this is really a good field to be in is that some of the work can be done with, you don't need high-tech or a very highly equipped lab to be doing these measurements, because as you know from graphene, essentially the single layer was just made with the Scotch tape, right? And van der Waals materials are basically materials that are held together by the force that is holding them together is weak, and so they can be taken layer by layer apart. And of course, they have phenomenal properties, some of which I'll talk about. So there's a whole series of these materials, and the ones that I have been involved with mostly have been either hexagonal boron nitride, and I'll give you one example of that, or these transition metal dichalcogenides. The dichalcogenides, chalcogenide here is sulfur, so there are two layers of sulfur, and in the middle of those two layers of sulfur is a layer of a transition metal, and in this case, molybdenum or tungsten. So these are really, you're looking at atomically thin, because even when you have these three layers here, they're still very thin. And of course, hexagonal boron nitride is just a layer in itself. It is very much like graphene, except that it's an insulator, while graphene is a semi-metal. But so what is so striking about these materials? One of the things that you find, the most striking one, is that when you go to the single layer, it becomes a direct band gap. Now again, if you're not in condensed matter physics, the thing about band gap is basically you heard this morning the talk about Fermi levels, and you know about what happens in Fermi level. It is a concept that comes about when you have a lot of atoms together and they're making either a nanoparticle or, in the early days, bulk material, right? So Fermi level basically tells us that if it is a metal, then all the energy levels below it are occupied and above it are unoccupied, right? In the case of a semiconductor, it's not so much the concept of Fermi level, but in semiconductors, we have a valence band, and that is all the levels up are occupied there, and then you have conduction band, which is unoccupied, and they're separated. So there's a band gap. And as you know, all of from transistors, from anything that we know about solid state, that band gap makes a difference, right? Because that basically means that it's a switch. If you've got enough energy to take something, an electron, from one level to the other, you will see the one effect. If you don't, then it will be the other. So switches are very important, and that is what a lot of condensed matter is really about, is creating this possibility to tune things. So what happens here is that in this material, if you have two layers, then you have an indirect band gap. And again, basically that means that you need a phonon of the system to do the excitation, whereas in a one layer, it's a direct band gap. So again, you can see that if you go from a single layer to a double layer, you can basically change many features. You can change transport features, right? Conduction, which is really important. And what is also important here is that this band gap in these materials it lies in the visible. So that's why there are all kinds of prospects for it, because if it's about 1.8 EV in some materials, 1.6 in others, and so on. So it's in the visible, which means that a lot of applications there. Okay, so the other is that the photoluminescence in this is very large, and more importantly, these particles called excitons, which again, goes down to the legacy of Bose. Exciton is a boson because it has what is it? It's basically an electron. When you have so you have the semiconductor, right? So in a semiconductor, this is your valence band, and this is your conduction band. This thing here, when you take an electron from here and put it in the conduction band, you have left a hole over there. But that electron remembers where it came from, and that electron and hole, basically, because of Coulomb interaction, there's a coupling between them, and then they travel together in the material together as a single unit, and these are called collective excitations. There's a lot of theory that goes behind this. In fact, calculating properties of excitons and from ab initio, which is the kind of work that I do, is non-trivial. But we have succeeded in doing that. And so these materials show excitons which have very large binding energy. The reason I wanted to bring to your attention semiconductors that you're familiar with, silicon, gallium arsenide, and so on. In those materials, the binding energy of this exciton is in millivolt, very, very small. Okay, so you still use it for various purposes, but not as much opportunity as you have when the binding energy is so large. So here the binding energy could be as large as half an EV. So you're talking about difference between 5 milli EV to 0.5 EV. So that's several orders of magnitude difference. And then they have other quasi-particles as well. There could be 2 electrons connected with a hole, or there could be 2 holes connected with an electron, and so on and so forth. So you get these other excitations, which are tryons and biexcitons and so on. And these are all observed and being used for various purposes. So just for your information here, I thought I'll show you a little bit about what else can be happening with excitons and why these materials that I'm talking about are so interesting. You heard yesterday the talk by Dr. Hassan, and he was talking about topological insulators. In these materials as well, one of the most important thing is that spin-orbit coupling plays a major role. Okay, so what does spin-orbit coupling do? Spin-orbit coupling, essentially, as you can imagine, it causes a splitting, right? Because, instead of J being the quantum number, right, L plus S is J, and L and S decouple, and of course that happens when there's some kind of symmetry breaking in the system. So what is the symmetry breaking in this system? If you take a hexagonal, actually, let's go to transition metal dichalcogenide, which has a sulfur layer and a molybdenum layer, let's say, and a sulfur layer. If you look at it from the top and from the bottom, it's not, there's the reflection symmetry is lost, and that loss of reflection symmetry actually gives rise to these levels. So what you have here is that it is almost as if the spin, these levels are split as a result of the spin. So if this is spin up, then that is spin down. And so what happens then is that now this electron and hole, the exciton that you're talking about, instead of, if they have the same spin, then that is the direct exciton we talk about, and that's the one that typically happens in most materials. But in these materials, because of the spin-orbit coupling, you can have the situation where these particles here, again, they're exciton, but transition or their recombination could be forbidden because of spin. It would be a violation of the spin, or it could be because of the momentum. So, for example, the electron here and the hole there may have different momenta, in which case also that will be a momentum forbidden transition. And so these lead to, of course, very different kind of dynamics of the system. And mainly what I wanted to show you here is that what happens then is that this is if you did not have spin-orbit coupling, this is what the band structure would look like. Again, these are the bands, these are the valence bands, these are the conduction bands. If you have spin-orbit coupling, then you see these levels split, and then of course there are transitions between them, which are all then observed experimentally. But one of the questions that happens here is that if you just look at these, if you look at the energy levels are the same. So everything here is at one energy level, and then everything here is at the other level, right? This is the top of the valence band, this is the bottom of the conduction band. But what happens if you look at this one and this one, they're at the same level. Experimentally, they find a difference of 10 millivolt. So part of what our job was, one, to calculate the properties of these excitons. And even though electron and holes interact with Coulomb interaction, it's actually non-trivial, because in condensed matter physics, what you have is something called screening. One electron, it doesn't interact with all the nuclei or other electrons directly, because there's a sea of other electrons present, right? So that screening, how much of screening is in a system, really then determines the properties of that material. And what happens in this case is basically then we do something which is called density functional theory, which is a poor man's version of Schrodinger equation. You're trying to solve Schrodinger equation with many, many electrons and protons and so on. And so there are approximations that are made that I'm not going to get into. So we do these calculations with density functional theory that gives you the excitations in the various the ground state properties of the system. But that collective behavior, so when we have an electron coupling with a hole, and this is all dynamical, that collective behavior cannot be represented by density functional theory. What we do is we use time-dependent density functional theory, and it is not just the time-dependent equation, but rather it allows you to take into account what we call exchange correlation functional. And again, those are very many details which I'm going to skip, but that has been a major effort in trying to calculate these quantities. And what we were able to show is that when you have, so this is your hole here, and now the electron could be either in this valley here, let's say this is a spin down, and let's say that is spin up. So it could either go to that valley or the other valley. And depending on which one it is coupled to, the energy will be different, and we trace that energy difference to the exchange interaction, okay? Exchange interaction as in Hartree-Fock exchange, all right? So once we do all those calculations, we come up with actually an answer that is remarkably close to experiments. So experiments find the difference in energy between these two types of excitons. Now, how do they know that? Well, one of them is visible directly. The other one is visible only when you apply something like a magnetic field, or there are other ways of getting the indirect exciton. So, but they find the energy difference to be 10 millivolt, and we find it to be about 20, something like that. So that basically shows that the calculations that we are able to do now, which again has been many years, for about 50 years of advancement, that we are able to reproduce properties of these materials in a pretty reliable way. I will give you one more example, and then I'll switch over to chemistry, but again, thinking in terms of Bose and paying homage to Bose, there's one other work that we did with excitons, which actually we would not have been able to provide a solution directly unless we thought in terms of fermions and bosons, and I'll tell you in a minute what I'm talking about. So essentially what happens here is that they are looking at these materials. So they did this molybdenum disulfide, this material that I was mentioning, which has a layer of sulfur, a layer of molybdenum, and a layer of sulfur. All three layers, in all three layers, the atoms are arranged with hexagonal symmetry, and one on top of the other. And again, lack of time, I'm not going into details. But basically what happens is that when they look at the photoluminescence by changing the isotope. So they took three masses of molybdenum, and here I'm showing the result for two of them, and they found a shift in the energy at which you can get this photoluminescence. Now, why is that important? Because what we are trying to do with these 2D materials, if you want to apply them for solar cell or some other purposes, is that you want to have a range in which you can actually be varying the energy at which the absorption or the luminescence will take place, okay? So basically, then what they looked at is that they found that the shift was actually a red shift with when the mass was increased. And again, without providing you any details, let me just tell you that if we think about the interaction between electrons and phonons, which is, you've heard in other talks too, the interaction between electrons and phonon is something that is responsible for BCS, right, for superconductivity. So here again, if we think in terms of the fact that we have electrons in this material and they interact with phonons, we would not be able to show that this shift this is a red shift. What one expected was a blue shift. Again, why? Because phonon frequency, you know, it goes as what? Root k over m. So m is in the denominator, And as the mass increases, the frequency decreases. So that's one hand-waving way of thinking about it. So then we went through this calculation and basically tried to answer these questions that how is our phonons affecting the optical band gap? How do these isotopes, how do the exciton binding energy, how is that modified? And then what are really the oscillator strengths that, because, basically you're looking at absorption of light and emission of light, right? Interaction of light with matter, and how does it all come about? So essentially, what you find is that if you change the mass, it doesn't change the band structure at all, right? Because band structure of a material is a property of electrons and not of the nuclei. But then and again, I'm going to skip this. You then go ahead and calculate the electron-phonon interaction, and you do the phonon spectrum. You then look at how the phonons, the different phonons that are dominant in these systems, how they couple, and you see that, yes, there is a shift, and the shift is the opposite to what they see in experiments. What did I do? Okay, so basically then, so what is happening now is that you have the electrons and the holes, you've got the conduction band and the valence band, and then of course electrons interact with phonons, holes interact with phonons, and there's a renormalization of the band gap. And that is where the anomaly doesn't occur. When we include now that this electron and phonon and hole, they are not running around independent of each other, but rather they are bosons, and they are coupled with each other. When you do that, when you take into account the boson statistics, and then you calculate exciton-phonon interaction, then lo and behold, you come up with the right answer. And again, for the purpose here, all I will say is that we get that so that as we increase the energy, the binding energy changes, and as a result, you get the red shift that the experimentalists had observed as a function, as they changed the mass, as they increased the mass. So this was actually, and not just that, but again, qualitatively, we could reproduce almost all the features that they saw experimentally, which was really quite exciting, because what it told us is that the boson distribution is what we needed to do, because the electron and hole are moving as a particle with the spin 1 rather than spin half as it would have been for just electron. So anyway, I'm going to just show you here that basically this was one of the victories here, and but then I'll move on to, I think I have some time, I'll move on to talk about defects in 2D materials, and this is something that is just to show you how you can manipulate the electronic structure. So I think my original talk was tuning, so most of the work that I do, and a lot of us do, and we do it together with experimentalists, this is basically called designing novel quantum materials, okay? And how do you design novel quantum materials? Well, what knobs do you have with which you can design things? You can change the electronic structure, right? You can change the spin orientations. You can change spin-orbit coupling. So these are basically very fundamental quantum mechanical properties that when you do enough of a study here, you get an idea about what material or what atom or what element to use in these 2D materials or 1D materials that will allow you to then give it resultant properties that have characteristics that you are interested in. So this one is now a physicist trying to do chemistry. And here, what I'm showing you here, and I probably don't have to show much more than that, that when you take hexagonal boron nitride, and here what we have done, so that is just boron and nitrogen atoms arranged in a graphene-like structure. And if I take one nitrogen atom out, I end up creating a local inhomogeneity, right? I end up creating an electronic structure where you have now depletion of charges in one place and addition of charges in the other. Basically polarization, okay? Basically dipole moment. So it goes back to very basic physics that by doing that, what you end up doing, and this is again, I'm going to skip that, and what you end up doing is creating a scenario where something as important and challenging as carbon dioxide can be converted into something like methanol, okay? This is one of the big challenges. Of course, we've had a major change of government in the US, and so I'm not sure what's going to happen in January, but the big initiative under Biden was this Clean Energy Initiative, and so essentially the idea was that you have all these gases around, CO, CO2, and you want to convert them into value-added products. So that's where a good bit of my funding also comes from. And so we are looking for catalysts. Now, what do we mean by looking for catalyst? And that's where physicists come in, because the catalyst is the material. And so in a sense, I'm a material scientist. And what a catalyst does is provides you alternate ways by which you can reach your destination, right? It's almost like going for a hike, and you can go over a mountain one way, or you can find a path around, and you can get there without bothering yourself too much or getting too tired, right? So that's basically what a catalyst does, is finds you another pathway. And how can a physicist do these problems? Well, all of it has to do with energies, right? You can calculate energies. Potential energy is what we are calculating in all of these. So you need to know how atoms and interact with each other, how they interact with the electrons, interact with holes or with nuclei and so forth. So, and then you need to know statistical mechanics, right? And so if you put all of these things together, then you have all the tools that you need theoretically to do chemistry, and basically the other thing is that what we are trying to do is, again, as I said, we are trying to change the electronic structure, and what you find is that if you can manipulate things so that, for example, this is what a metal looks like, this is what a semiconductor looks like. What do I mean by that? What I said early on, that in a metal, you have all levels occupied up to the Fermi level, and these are unoccupied, right? But there's no energy needed to go from here to there, just there. But then in a semiconductor, of course, there's a gap here. But then by either creating vacancies or defects and so on, you can actually create these states which were not there, and that then allows you to play God. I mean, you can basically create materials where you have distributions of electrons. These would not have been, so whenever you see this red and blue and so on, that means depletion or addition of electrons, accumulation or depletion. And once you have that, essentially, you have created polarization, you've created a dipole moment, and then interactions can happen. And that is that's basically what happens in these cases. And so if I look at this hexagonal boron nitride, the example that I gave you, where you could create various types of defects, and again, just bear in mind, let's just take this example, where I've taken that nitrogen atom out, the one I showed you. Then essentially what you get, and this is probably going to make some sense to those of you who are doing condensed matter physics, is that we have now created states. So if you see here, I've created an occupied state with one spin polarization and an unoccupied state with an opposite polarization. So in other words, you can go from here to there with a spin-flip transition. These, again, are responsible for a number of emerging properties of these materials, okay? So let me skip that and then basically show you what happens in this case. And essentially what you have here is that carbon dioxide is coming to this boron nitride with a, as you can see, as it approaches, it is wrapping itself up. Now, carbon dioxide it's carbon with 2 oxygen atoms like that, right? So it doesn't like to interact with anything because it's pretty comfortable being that way. The only way carbon dioxide interacts with something is if you're able to bend it. And when you bend it, then you can grab one of its oxygen and the process can go on. So what has happened here is that charge that was there, this carbon dioxide has got itself wrapped around it, and so you see the bending has happened, and now it's there, and very soon it is adsorbed on the surface. Okay? This is all quantum mechanics, all right? Now we go to another one. Carbon dioxide is already sitting on that surface right here, and now I'm going to bring hydrogen, right? Because CO2 and H2, right? And now you can see what's going to happen. It comes in, and of course it takes a certain amount of energy. That's the barrier. It goes up there, and there now it starts to break up. So as you see, once hydrogen got that energy, it actually came, and it is now coming and sitting very close to the carbon dioxide, which is already on the surface, and it is now in that form. So basically then, and this I will not go into details, but what I have done here, just to convince you, is that we go through, we calculate all the various paths that can happen, all the products that can take place, and one prediction is that you can get methanol from it or you can get formic acid, all right? So let's just say that somehow I've done all the calculations, and then the experimentalist who we were working with, he was able to show, this is Richard Blair, that indeed what he gets in his system when he takes hexagonal boron nitride, he does ball milling, which creates defects, and then what happens is that you then create methanol. So this is essentially conversion of carbon dioxide to something useful. Okay, I don't think I have too much more time. Do you have about 5 minutes? It's okay, 5 more minutes? I should be closing. Okay, so this one I will skip because this was I will just mention that what we are doing now is instead of having these 2D materials, we are also thinking in terms of just single particles. So this is a single atom of palladium or platinum. And again, we can go through the same kind of argument, and you can see that we can show, and I'm going to skip all of this, and you can take it later. We can actually use this to convert, again, methanol. This is the opposite reaction. We can use this to get hydrogen from methanol. And again, it is done experimentally, and also we can show that theoretically. So let me just come back to the last thing, and I'm going to skip all of this, and to the last topic that I had. And this is, of course, all of my colleagues from various places who have made this possible. On this side here is my research group. Naseem, by the way, is from Pakistan, and now I have Faiza and Bushra also from Pakistan. So it's quite an international group, some people from Iran, other colleagues here. And I should mention Alamgir and Audience used to be also in my group. But what I've thought I will spend just 2 minutes on before I sit down is that there's an effort that some of us have been trying to push, and this is to how do we broaden participation. And the broadening of participation means in many ways. In the US, it could mean bringing in people from underrepresented minority groups. We have programs that by which we have been very successful in that effort. And there are some things that we have learned about how you bring in people who are not already in the picture or ready to become scientists. All you need is a little bit of effort, and they are able to participate. I just wanted to share with you some things that we are doing in Karachi, and which is also, from Dhaka. I went over to Karachi before going to the US. And something that we are doing there is enhancing subject content knowledge for teachers. And this is something where we have a center there where we're working with local school to high school physics teachers and chemistry teachers, actually. And so we've organized several workshops, and this I'm doing with colleagues from well, obviously colleagues from Pakistan, but also from the Netherlands, and majority of them from Oldenburg, where I spent my sabbatical. And we've organized several workshops there, and we do some things via Zoom, and others are, and they also have hands-on activities, and there's ongoing discussion. So this is one small way in which we are trying to see that we can form form an international network for enhancement of content knowledge of teachers, because once you have teachers who are more confident about the subject, then you can see how that can affect students in the same way. Another thing that is going on is with APS, but I can talk about it in another session. So thank you very much for your attention, and I look forward to your questions.
Quick questions, please.
Hello. Okay. Professor, since you have been working on AB initio calculation for a long period, so I think you are the right person to ask this question. Since a machine learning and deep learning is developing quite rapidly, and we are actually getting out of the barrier of the hardware, hardware barriers. So, what's your insight on the future of material design?
Right. So that's a very good question. In fact, I didn't have time to go into it. I think machine learning is something we can really take advantage of, right? So it is another tool. So what happens is that we collect. So for example, you saw that I was picking a transition metal atom, putting it on an oxide surface, right? So there are many oxides, there are many transition metals, many things can happen. So what you do is that you find a quick way to do these calculations. You want to see trends, okay? And where machine learning helps is to analyze data. Okay, and to actually look at data at places where you wouldn't see with your eyes, and you don't have enough bandwidth to do it in your calculations. Okay, so machine learning, if you train it properly, that's the most important thing, right? You have to train it properly. You have to train it to do the good things. You have to train it to do the bad things. Then what it does is that it can point you in the right direction, and you may discover even combinations of materials that you wouldn't have done otherwise. But machine learning has to be done with care and with the idea that it is a tool, it's your slave, not the other way around. So this whole idea that you apply machine learning to everything, no, you're not going to get anything. It's garbage in, garbage out. But if you use it with the knowledge that you provided, because you have to train it, then it can show you things that, it's almost like, you take off your glasses, you may not be able to see everything, right? I put on my glasses, I can see much better. So it's that kind of an idea. So use it with care. But yes, I think you should get trained in how to use machine learning and what are the because there are many, right? You do neural networks, there are all kinds of them. And yes, training is good, but use it with caution.
Any other question? Yes, please.
Assalamu alaikum. We are here from English medium schools. Me with Zakaria sir is here. So I'm actually talking about the STEM project you are doing in Karachi. Mm-hmm. The same thing can we do in Bangladesh for our school students?
Of course.
So how can we proceed for that?
Well, so one reason I wanted to mention it here publicly was that this is something that we are doing. We are actually now doing it. I'm also part of something which is called the Peace Institute. So there are also things being done in Africa and in several places in Africa right now, and there are efforts to do some things in Jordan. So yes, so we could definitely do, so the question is, what do we need for that, right? So first of all, people like me are useless because I don't live here. However, if you have local colleagues who are willing to get people together, because you have to find a way of getting the teachers, and then you have to find a way of engaging them. We can provide all the material. We can do things by Zoom. We can also come and do it physically. We can be here. But what we need from people locally is the contact with the teachers. And if that is there, I'll be happy to talk about it. But I think this is something we want to take across the world. Yeah.
Yeah, thank you so much.
So I think we should Professor for the nice talk. So the next second talk of the session is by Muhammad Asad-ul-Zama, and the title of the talk is Dipolar Bose-Einstein condensates.
Thank you. I'm Muhammad Asad-ul-Zaman, and I'm happy to be a part of centennial celebration of Bose-Einstein statistics, and thank you very much for inviting me. In this talk, I'm going to talk about dipolar Bose-Einstein condensates in the mean field approximation. I believe you already heard what is a Bose-Einstein condensates, and I'm going to go through it again. So in order to get there, I'll be talking about some temperature effect on matter, and then a little bit about simple harmonic oscillator. Then, in order to understand the dynamics or full dynamics of a Bose-Einstein condensate, we need to understand the ground state properties. I call here stationary properties of a Bose-Einstein condensate, or BEC. So in order to get that, we have to solve Gross-Vitebsk equation. And for the excitation spectrum, we need to see the dynamical properties. And for that case, we have to solve Bogoliubov-Digens equations. And then finally, I have to talk about the dipolar Bose-Einstein condensates in a WL type of potentials. So first, the effect of temperature. At very high temperature, we don't have atoms, we have only ions. They are at very high velocity, and we call that state plasma state. If you lower the temperature, we get the gaseous state, and if you decrease the temperature further, we get liquid, and at very low temperature, the usual state of matter is solid. But Bose-Einstein condensate, you have to get it at very low temperature, and it's a gaseous state. So it must be a metastable state, and you have to engineer something in the laboratory to get that special state of matter. So here are the statistics of fermions and bosons. And the main difference here is the occupation number. Ni is given by that thing. Ei is the energy of that state, and mu is the chemical potential energy. Kb is the Boltzmann constant, and T is the temperature. The main difference between these two, Bose-Einstein statistics and Fermi-Dirac statistics, is a difference of -1. If the chemical potential is equal to the energy of that state, the factor goes to 1, e to the power 0 is 1, so Ni should be half. But on the other hand, for the boson case, when this factor is close to 1, a macroscopic number of particles can occupy a state with that energy, or we can say the ground state can be occupied by a macroscopic number of particles, and that is the Bose-Einstein condensate. So in order to get a better idea, it's better to look at our beloved simple harmonic oscillator. This is the usual Schrodinger equation, and it's the linear Schrodinger equation. I express everything in unit of oscillator energy scale and oscillator length scale. So it's a one-dimensional harmonic oscillator. Energy states are symmetric, antisymmetric, etc. And here, if you load a trap or harmonic oscillator at very low temperature, I'd like to say at absolute zero temperature, the fermions occupy each state with occupation 1. That's called degenerate Fermi gas, and this is a very active field of research. And here, for the bosonic case, look, the ground state can be occupied a macroscopic number of particles, which is the Bose-Einstein condensate, and it was predicted by Hassan Bose and Albert Einstein in 1924, exactly 100 years before this year. So Bose-Einstein condensate is a gaseous state. In order to have a better idea, if you look at the Bogoliubov-Digens wavelength, which is given by Planck constant by the momentum of the particle, and at very high temperature, particle momentum is large, and Bogoliubov-Digens wavelength is, de Broglie wavelength is very small. That means de Broglie wavelength gives us the extension of the particle. So if temperature is high, momentum is large, de Broglie wavelength is small, and particles behave like a particle. On the other hand, if you decrease the temperature, de Broglie wavelength comparable to the interparticle separation, and they extend more. And if the temperature below a critical temperature, the wavelength becomes much larger than the interatomic particle, and they form a macroscopic matter wave, which is, we call it Bose-Einstein condensate. So here is the theoretical description. If you consider n number of particles in a trap, this is the kinetic energy term, this is the external confining potential, and that is the interaction term. Even though Bose-Einstein condensate is a very dilute gas, interaction between the atoms play a very important role in the dynamics of the Bose-Einstein condensate. But at low temperature, the actual potential can be replaced by a pseudo potential, and here is the scattering length. People set that to a value which can be obtained using the first Born approximation. And here is the Harty approximation. The overall wave function must be direct product of individual wave functions, and we get that equation. This is called the Gross-Vitebsky equation or Schrodinger equation for Bose-Einstein condensate. Here mu is the chemical potential energy, and this term, which is the interaction term, it depends on the number of the particles and scattering length, and it depends on the density of the wave function. So here is the image of the first BEC in the laboratory. The Bose-Einstein condensate was predicted in 1924, but since it's a very delicate state of matter, it took more than 7 decades to realize that thing in laboratory. So first observation of Bose-Einstein condensate in 1995, I believe is Eric Cornell's group. So that false color image showed that it's a decreasing temperature in that direction. So at relatively very low temperature, this peak indicates that the macroscopic number of particles are occupied by the lowest state, and that's the signature of the Bose-Einstein condensate. So these 3 groups, within few months, they realized these Bose-Einstein condensates led by Eric Cornell, Randall Hewlett, and Catterley. But physics Nobel Prize goes to this Eric Cornell, Carl Weyman, and Wolfgang Catterley for 2001 Nobel Prize in Physics. So Bose-Einstein condensate is very important for 2 reasons. One, it's a fundamental physics question. The second, sorry. So the second, we can model many condensed matter physics experiments in using Bose-Einstein condensate and general Fermi gas, because it's a very clean system, and you can control each and every parameters independently. And this is basically meant to, because of the manipulation of laser and optical lattices. And now I consider dipolar Bose-Einstein condensate, and dipolar is very important compared to that short-range interaction case. This is the interaction in alkali metals is mostly two-particle interaction. It's a very dilute gas, and it's kind of a contact interaction. And this interaction is it doesn't that much depends on the trap geometry. On the other hand, this is the dipole potential. It's anisotropic and long-range interaction. On the other hand, this interaction is very short-range because it's van der Waals type of interaction. Here, this is the dipole strength, and theta is the angle between the dipole direction and the radius vector r. So when we consider the dipolar BEC, the trap geometry becomes very important, because when two dipoles sit side by side, they kind of repel each other. On the other hand, if two dipoles are in a head-to-tail configuration, they attract each other. That means by using the trap geometry, you can effectively control the interaction between the dipoles. So here is the Bose-Einstein condensate of chromium atoms. Chromium atom has a large dipole moment, and this is the effect of the trap geometry. So the first few dots for the BC, they take the picture after turn of the trap. So the BC is released from an isotropic trap, and this set of pictures from an isotropic trap. And you can clearly see there is a huge difference, and there is another set of data, and these are the experimental data, and this is the theoretical predictions. So there is a one-to-one correspondence between the experimental data and the theoretical predictions. So dipolar Bose-Einstein condensate is very rich, the physics of dipolar Bose-Einstein condensates, and here, this is the mean field study shows that this is a phase diagram, dipole strength in that direction, and this lambda is the trap aspect ratio, and trap aspect ratio is defined as omega g by omega rho. These are the frequencies in the z and rho direction respectively, and when lambda is less than 1, that means the frequency in the rho direction is more than the frequency in the z direction, and particles are allowed to move more in the z direction because of the low energy. On the other hand, if the trap aspect ratio is large, this omega z is large compared to omega rho, as a result, particles are allowed to move in the rho direction. So particles feel more repulsive interaction. So what is interesting here, this green, I believe it's green or whatever color, that is the stable region, and there are some small islands where the density maxima is not at the origin. Density maxima are away from the origin, just like a red blood cell kind of structure. So we extend that thing in a double well potential. So this is the governing equation. This Hamiltonian consists of the kinetic energy, external potential energy, and one particle interacts with the mean field produced by n-1 number of particles, because we are considering n number of polarized dipoles in the field, and the external potential here, this is the usual harmonic potential, and we put a Gaussian barrier to create the create a double well. And look, this equation, this is the interaction potential, and it's not depend on the density, but it's rather depend on the density distribution. So it's a integral differential equation. It's difficult to solve directly mathematically. We have to solve it numerically. So here the important parameters are number of particles, trap aspect ratio, and we can tune two more parameters, the barrier height and barrier width B. So this is the double well potential, is the usual simple harmonic potential plus a Gaussian barrier at the middle that gives us the structure of a double well potential. And for the dynamical case, we have to solve this coupled equation. All need to see this. What we're trying to find is f of r, which gives us the density perturbation in the dynamics of the Bose-Einstein condensate. So here is the main finding. Here, this is the trap aspect ratio as a function of the dipole strength. We have very interesting things here. This S means the ground state solution is symmetric. For this small case, it's symmetry broken. That means dipole occupies one of the two wires, and this part is, and that part is unstable. And if you look at this thing, particularly point 1, that means G direction is soft compared to the rho direction. So particle can sit on top of each other. So if I move in that direction, the solution occupies both of the wires. Then because of the strong interaction, as we are increasing the dipole strength, the wave function occupies one of the wires. And after that, it's unstable. For the isotropic case, that means lambda equals 1, the solution is stable, symmetric. They occupy both of the wires and then unstable. And for large lambda, say 10, where the interaction is mostly repulsive interaction, the dipolar BEC is stable because look at the x-axis or the horizontal axis is the dipole strength. And we found small islands where the structure is not Gaussian and it's like red blood cell structure. So what does that mean? Here, I take a small lambda value wave function. This is the contour plot of the wave function as a function of z and rho. The wave function occupies both of the wires, and they are extended more in the g direction. It's -2 to -4, and it's less extended in the rho direction. And there is another snapshot. It shows that the wave function occupies only one of the wires because of the attractive interaction. On the other hand, here, the wave function is symmetric, and here lambda is large. That means wave function extends more in the rho direction than in the g direction. And I take a picture from this small island. Look, the wave function maximum is not at rho equals 0. It's away from the rho equals 0. That gives us the structure of a red blood cell. So here, this is the dynamical properties. So wave function oscillates in both of the wires symmetrically. Here, wave function oscillates asymmetrically, and the system collapses through softening of one of the modes. These are the eigenfrequencies as a function of dipole strength. And we also analyze it directly by observing the Josephson type of oscillation when for small lambda value, when wave function occupies both of the wires, there is oscillation between the two wires. It's a tunneling thing. On the other hand, when it occupies one of the wires, there is no oscillation between the wires. It's a in-wire oscillation. Now, for large lambda value, specifically for lambda equals 5, these are the excitation spectrum, and the system collapses by a different mode. And it can oscillate between the two wires, as well as there are some nodal lines in between the two, in between the density perturbation. Then we play with the barrier height for moderately pancake shape. That means lambda equals large. Here, we plotted the dipole strength and as a function of the barrier height. This is lambda equals 6. So because of the long range interaction, the system unstable for very small d, but if we increase the barrier height, we can stabilize the system. This is lambda equals 8, almost same behavior, but it's stable for a large dipole strength. And interestingly, we found a very small island, which we call unstable island or instability island. The system is stable everywhere except that unstable region. And here, the same phase diagram for lambda equals 9. So it's more stable as a function of dipole strength. And the density distribution is very important here. We can control the dynamics of one BEC by another one because of the long range dipole-dipole interaction. We have this structure where the density maxima is not at the center. We have ripples type of structures, etc. So here is the instability island for a particular lambda value, here D. So everywhere the system is stable. But for this small island, the system is unstable. So this is because of the softening of this particular mode, which reappears. If I go from this side, it's stable, stable, and collapses here, and it reappears from that one again. This is the excitation spectra for that particular case. Then we analyze, since the dipole-dipole interaction is long range, how to tune one dipolar BEC by the presence of the another one. So in that case, we have to solve the coupled Gross-Pitarevsky equation. So we assume each trap occupies same number of dipoles. This is the wave function in the J well. This is the usual kinetic energy plus trap potential energy. It interacts with n j minus 1 particles in the same trap, and it interacts with n number of particles in the other trap. And again, these are integral differential equation, and we're playing with the trap separation, which is defined by the absolute value of the trap center difference. So here is the manifestation of long-range dipole-dipole interaction. Since I have two different traps and they interact by the dipole-dipole interaction, and dipolar interaction can be attractive or repulsive, we define a quantity asymmetry parameter. So density is on the same well, density with respect to the origin of the trap, and look, the density is not symmetric. As you increase the separation, and this time B is the separation, and we're plotting is the inverse separation. That means when it's 0, they are infinitely separated, and as if we have two independent dipolar Bose-Einstein condensates, as we bring them close to each other, they feel, even though they are in different traps, they feel each other, and wave function started away from the symmetric case. And here are the phase diagrams for coupled dipolar Bose-Einstein condensates, and this is effect of the second dipolar BEC. Look, if the separation is 0, they are uncoupled case, particularly at this case, I believe lambda equals 15, where the dipole-dipole interaction is mostly repulsive interaction. So when they are infinitely separated, it's stable up to 150 unit. On the other hand, if we decrease the separation, the stability decreases dramatically, and if the separation is kind of appreciable close to each other, it destabilizes at around 40 dipole strength. So we can tune the dynamics of a dipolar Bose-Einstein condensate by using another dipolar Bose-Einstein condensates. Here is the excitation spectrum. For the uncoupled case, is stable up to dipole strength 50. On the other hand, if they feel each other in the due to its long-range interaction, is unstable up to that point. And we can use dipolar Bose-Einstein condensates in many different ways, because many condensed matter physics experiments can be modeled using any Bose-Einstein condensates loaded into optical traps or optical lattices, also with the degenerate Fermi gases. That's why Bose-Einstein condensates and degenerate Fermi gas are very active field of research. And many people are doing many things, and there are many things to be done. Thank you very much. And I did this work with Dr. Bloom. She was my PhD supervisor, and it was funded by National Science Foundation USA. And some of the pictures are taken from internet. Thank you for your attention. Thanks.
Professor Asad-Zama would be happy to entertain a couple of questions. Can I have
Thank you.
ask one
Yes, please.
question? So you talked about this. First, you talked about one component Gauss-Pitowski equation, and then you moved on to a coupled Gauss-Pitowski equation. So these two equations are these equations for scalar Bose-Einstein condensate or spinor Bose-Einstein condensate?
They have
Dipole.
dipole moment,
Yeah.
and they are polarized.
Polarized, and
Yes.
what is the spin of the atom?
Sorry?
Spin,
Oh, spin has to be any integer number.
any
because these
integer
are,
from
bosons.
0 to
Yes,
onward.
yes.
So the first equation, which is one component,
Yes.
is non-linear Schrödinger equation, and
Yes.
non-linear Schrödinger equation has an exact solution.
It doesn't have, but except for few cases,
Yeah.
if this
When you
it doesn't have that integral part,
Yeah.
we can have the usual non-linear Schrödinger equation, which depends on the density only, and we have many solutions, exact solutions, like
Yes,
solitons,
yes,
peregrine
yes.
solitons.
So you
etc.
take that kind of approximation.
No, I didn't do any approximation. I solve it numerically.
Okay. Okay. Thank you.
Thank you very much.
So if there are no other questions, we will thank again Professor Asad-Zama. Thank you very much. So the next last talk of the session is by Sumati Rao, and the title of the talk is Beyond Bose-Einstein Statistics, Majoranas and Parafermions. Please.
I'd like to begin by thanking the organizers for giving me this opportunity to talk over here. What I'll be talking about is beyond Bose-Einstein statistics. So essentially, I'll be talking about what are called any-on statistics. The plan of my talk is to basically, I'll just first give a brief introduction to what you all know, which idea of indistinguishability of particles, and this is what leads to something called any-on statistics. And then I'll go on to generalize that to non-abelian statistics and what are called Majoranas and parafermions, and explain why they are so relevant now in the terms of quantum computation and topological quantum computation. I'll discuss briefly where to find them, and then our focus, which is on the quantum Hall edges, and then very briefly explain what happens for realistic edges and when Coulomb interactions are taken into account. So to start with, as we've all been discussing since the beginning of this conference, all elementary particles are either fermions or bosons. And when identical particles are exchanged, all we can say is that one particle is at position R1 and one particle is at position R2, but we don't know which is which. So how are the wave functions then related? The wave function of where particle 1 is at position R1 and particle 2 is at position R2, as compared to when particle 1 is at position R2 and particle 2 is at position R1. We know that for bosons and fermions, this is where the difference between normal Maxwell statistics and this comes, that for bosons, psi R1 R2 is equal to plus psi R2 R1, whereas for fermions, it is minus psi R2 R1. But, and this is true for all naturally occurring particles, but for emergent quasi-particles and condensed matter physics, we don't need to be restricted to this. The simplest generalization that one can think of either bosons and fermions is just what happens if you introduce an arbitrary phase, e raised to I theta, when you exchange two particles. So this is the simplest generalization, and this is what are called abelian anyons, and was introduced by Linus Boehm and Wilczek, later on Wilczek in 77. And why is this possible? As we'll see, it's only possible in 2 dimensions, because in 3 dimensions, any loop which is formed by the exchange of any 2 particles can be taken off the plane and can be contracted to a point. But in 2 dimensions, if we try to exchange, if we try to take one particle completely around another and try to change the path, what you find is that you'll have to go through the other particle. There's no way to kind of contract this. Here you can take one particle around the other and take it off the plane and contract the path to a single point, but that's not possible over here. So due to this, this is what leads to anyon statistics in 2 dimensions. Mathematically, the distinction, that is, if you remove a single particle, an origin in 2 dimensions, it makes the space multiply connected. You can have paths which go around the origin a number of times. You can actually count the number of times you can go around the origin. And that's why even if you exchange 2 particles, even if you exchange them multiple number of times, you will never come back to this. You can always distinguish this configuration from one where you've not exchanged. Whereas in 3 dimensions, you know that for fermions and bosons, once you've exchanged the particles twice, after that you can't tell whether you've exchanged it or not. So in 2 dimensions, what happens is that particles are classified in terms of the braid group and not the permutation group. So this is the distinction in 2 dimensions, and which leads to anyon statistics in 2 dimensions. And the quantum statistics that is obeyed by anyons is very different from bosons and fermions, because it's precisely, you cannot write down a symmetrized or an anti-symmetrized wave function once you introduce many particles. You cannot forget that you've exchanged. So it's as if the entire history is important. So it's like a very complicated many-body problem. Even the simplest free anyon problem is actually a many-body problem, because you have to know how it exchanged in the past with all other particles. So it becomes very hard to solve even for a system of free anyons. In fact, non-abelian anyons are a generalization of this, which makes it even tougher. It doesn't just acquire a phase under an exchange, which is what is true for abelian anyons. You actually, for non-abelian anyons, you need the ground state to be degenerate, and we actually exchange of non-abelian anyons leads to a rotation in this ground state manifold. So if I exchange, say, something like a 2-component or an n-component wave function, this will lead to a rotation in the unitary space. This was also introduced very early, but came to be used much later. What are Majorana modes? They happen to be the simplest of these non-abelian anyon modes. Majoranas, as many of you may know, was originally introduced in high energy physics as possible elementary particles which can be their own antiparticles, as candidate neutrinos or possible supersymmetric particles, neutral Higgs, etc. But in condensed matter systems, they're actually not even fermions. They're called Majoranas simply because they're self-conjugate. They behave actually as non-abelian anyons. And the simplest model that you can think of for Majorana modes is something called the Kitaev model, which was introduced by Kitaev in 2001. It's like the icing model for Majorana modes. And I've written it in terms of the second quantized notation, which may not be familiar to everyone, but I'll explain this briefly in the next slide in just pictures. This is the chemical potential. This is the hopping term, and this is what is called the pairing term. And the point is that this is a fermion, the creation and annihilation operator for fermions, and they can be written in terms of 2 real Majorana operators, gamma A and gamma B, which are self-conjugate, they're real. So in terms of pictures, what you can think is that you can think of the fermion at each site as being made up of 2 Majoranas. And what you want to do is change parameters of the theory such that these, right now when you think of it as a particle on a single site, and then you manage to change parameters so that the fermions actually get fractionalized and the Majorana modes get separated. In terms of this simple Ising model-like picture, it is very easy to show that when mu is less than 0 and t is delta is equal to 0, then the only modes between the same site particle. And in the other case, when mu is 0 and t is equal to this delta, you can rewrite this model in such a way that it looks like, in terms of Majoranas, there are only connections between the Majoranas on next receiver sites. So what you're doing is, by changing these parameters in the theory, you're going from something which is a unique ground state and something which is like this, which has the Majoranas separated at the two ends. And depending on whether this long range fermion is either occupied or not occupied, you have two degenerate states. So turns out that the Hamiltonian has no dependence on the n Majoranas, as is hence independent of whether any non-local fermion you create from these two n Majoranas is occupied or not occupied. So this was Kitayev's magic trick. He managed to fractionalize the fermion and put the two ends of the fractions at two different ends of the particle. So they behave now as independent particles. When they were together, they moved as a fermion, but once they moved apart, they're independent now. So, and what is amazing about this thing is that when, in terms of occupation, you can always only have to go back to the fermionic language. So there are 4 possible states with 2 fermions if there are 4 Majoranas. But you can think of braiding them. The exchange of the Majoranas lead to rotations in the ground state manifold, which means that you can braid these Majoranas. You can exchange one from the other and go to a different state in the ground state manifold. And this is what is extremely important for topological quantum computing. The qubits are now formed by either the occupation or non-occupation of this zero energy state. It's a zero energy state because epsilon naught is 0. And the quantum gates that you get are the unitary braiding matrices, which can be thought of as the quantum gates. And the qubits and quantum gates make up quantum circuits, which are used in constructing quantum computers. So the main important point about using topological quantum qubits as opposed to just spin qubits or something like that is because this is a non-local fermion. If you have any disturbance at one end, it is not going to affect the occupation of the entire fermion because it's a non-local piece. So this means that it's extremely stable, cannot be disturbed by any local disturbances. Qubit is what is called topologically stable. So now one can wonder where to find or engineer these non-abelian anyons. The theoretical proposal was that we can do it in actually if you just have a superconductor, a semiconductor wire with a magnetic field. This can be used to kind of mimic the Kitaev model, and the tunneling from a normal lead into the end of the wire should give a signature of the Majorana mode, which should be a state at 0 energy. The expected zero bias conductance was 2 E squared by h. This was proposed by Luchin Sawa and Das Sharma and Oreg Rafael and von Apun in 2010. And there have been many experiments ever since to look for these Majoranas. And there have been many retracted articles as well. But it looks to me that finally Majoranas have been seen, because there's a paper in 2024 by Chetan Naik et al. From the Microsoft group, where the title of the paper is Indium Arsenide Aluminum Hybrid Devices Passing the Topological Gap Protocol. This has over 127 authors with 35 graduate students, and they have done a combination of local, non-local transport measurements. It looks like that there's a high probability of having actually detected a topological phase hosting Majorana modes. And they see it in roughly half of the 25 samples that they studied. I mean, they've written it very carefully because the original papers, many of them were retracted and so on. So they said that there's a high probability of detection of a topological phase hosting Majorana zero modes. And this demonstration is a prerequisite for experiments involving fusion and breeding of Majorana modes. So this is an extremely important experiment. So I at least believe Majoranas have been seen, but I should say that there's been no complete consensus yet, because the paper has been published, but unless another group sees it, and the point is, since Microsoft is a commercial organization, not all details have been revealed. And but the problem with Majoranas is, even if you have them, they're not, they're not enough to have universal quantum computation. You can't, just using Majoranas, you cannot form all possible unitary gates that you need for a quantum computer. So they have to, you need more, even more exotic anyons like parafermions and Fibonacci anyons and so on. Fibonacci anyons are the ones which will give you universal quantum computation. So that gives us the motivation of why we want to study things like parafermions. They're more exotic than Majoranas, and they cannot be realized in a free fermion model. The proposals for Majoranas involve just a semiconductor wire, but for parafermions, the building blocks themselves need to be quasiparticles, which are found at edges of quantum Hall, for instance. And as I said, the motivation is that Majoranas does not lead to universal quantum computation and does not allow for all possible unitary operations. Parafermions, you can get far more unitary gates, even though it's not complete, and it actually requires Fibonacci to engineer universal topological quantum computers. And this can be constructed using quantum Hall platforms. But I should mention that this is still in the range of proposals. Nobody has done this experimentally so far. Parafermion models, like the cation model, can be constructed by generalizing spin models. And the simplest, which may be familiar to people here, is the 1D chiral clock model with flip and shift operators. This is just the generalization of the Ising model, with except that you are now having sigma j, instead of squared is 1, is sigma j raised to n is 1. And for the simplest generalization, we will take capital N is equal to 3. And you can do exactly the same kind of Jordan-Wigner transformation to rewrite it. Like the Ising model can be written in terms of Majorana modes, the spin models can be written in terms of parafermion modes. And again, you can have the same kind of things, that you can have the edges, the spins at every site can be split, and the split spins can be put at the two ends of the, you can have what are called dangling parafermion modes, like you have dangling Majorana modes. And it's now n-fold degenerate due to the possible non-local eigenstates formed by these end modes. And you can ask where these states can be formed. You need to have quantum Hall systems, and that may not be familiar, but let me just say that what you need to do is you have a quantum Hall system with spin up and spin down, and these can be engineered by using different G factors and so on. And you allow for superconductivity. I mean, you proximatize them, put a superconductor and a ferromagnet or an insulator on top of the other. And in this gap, actually, parafermions can be isolated. And experimentally, it has now been found that you can have superconductivity and magnetic field in these kinds of systems. That much has been shown so far, though these kinds of things have not yet been found. And if this thing was a nu is equal to 1 quantum Hall state, then you would get a Majorana. If this is nu is 1/3 or 1 over n, then you would get a appropriate parafermion. So yeah, essentially backscattering at the superconductor and normal scattering at the insulator creates some kind of a bound state in this interval. And how will you look for the signals of Majoranas and parafermions in this? You can do it using Josephson effect, because normal Josephson effect is something which tells you that the current has to be proportional to sine phi. It's a 2 pi Josephson effect. right? Because this is the usual Josephson effect that you have. You have a Hamiltonian which is minus j cos phi, and the current is proportional to the derivative of this, so it's proportional to sine phi. And here, what will actually tunnel are Cooper pairs from one side to the other. You can think of it as Cooper pair tunneling. On the other hand, if you have a Majorana modes, if you have a topological superconductor, I should have written this as topological superconductor, then what actually can tunnel between the two superconductors is an electron. And what you get for topological superconductors with Majoranas is something called a 4 pi Josephson effect. This has been again looked for, and people have kind of seen it, but it's not completely confirmed, just the way the Majoranas are not completely confirmed. Because people sometimes can give other explanation for it. But there have been experiments which have seen this. And the problem with these kinds of experiments is that they can be fermion poisoning. I mean, external fermions can get in and then it breaks some of these things. So you can get something which is called a 4 pi Josephson effect. And if you have a parafermion on the other hand, what has been theoretically calculated is that what you will get is for instance, parafermions with something like a nu is equal to 1/3, you get Z6 parafermions, and these Z6 parafermions lead something called to a 12 pi Josephson effect. So this is a proposal. It's not yet been seen. And this brings us to what we have done in this field. That is, I mean, we've been working at quantum Hall and edge state reconstruction for a while. And the problem with the quantum Hall edges in general is that there is something called edge reconstruction, which says that an edge is not as simple as it looks from topology. There are other, I mean, a nu is equal to 1 system can also have nu is equal to 1/3 edges besides the it can topologically it's supposed to have just a nu is 1 edge, but you can also have 1/3 counter propagating edges, and these counter propagating edges can renormalize into a 2/3 edge and a neutral edge and all that. Many of these things have been seen experimentally in Weizmann and in other places. So this is something, since these are complications in the edges, what we wanted to see, the question was what happens to Majorana's parafermions in quantum Hall systems when there is edge reconstruction. And this is a recent work which has been done with Kishore Iyer, who's a student now in Paris. He was a visiting student of mine in ICTS. Soren, a faculty at ICER, and his student Amulya. And since reconstruction is inevitable in realistic quantum Hall samples made from semiconductor heterostructure, we wanted to see what happens in this case. And our main results is that the Majorana modes are robust to edge reconstruction, because even if you have Majoranas and you have this edge reconstruction, you still continue to have 4 pi periodicity. But the edge reconstruction leads to 2 independent Majoranas at each end. So, and you get, it's 4 pi periodic but with 4 different states corresponding to the occupation of fermions from 2 different Majoranas. But this is again, what is the experimental outlook and future studies? As I said, recent experiments have shown coexistence of quantum Hall and superconductivity, but many hurdles remain to see these kinds of work. And you have to, we are planning to do this also in graphene, because those are graphene edges where actually this kind of experiments have, some of these experiments can be more doable maybe, so we have to do that. And we also have to worry about whether the second Majorana can be used in specific ways. So this is this thing. So let me just summarize in the end and the takeaway points. What I have done here is discuss some new particles with abelian and non-abelian anyon statistics. And I've discussed why they may be relevant for topological quantum computation. I've talked about experiments to look for Majorana modes and the current status of these experiments, and discussed why we are interested in more exotic quasi-particles like parafermions and how one can engineer them in experiments in the near future.
Thank you very much.
I at least hope that we have convinced you.
Any questions?
Yes, please.
In learning quantum field theory, one comes across the spin statistics theorem, where you have either fermions or bosons depending on their spin.
Yeah.
And that somehow gets subverted in this two-dimensional picture. So what goes wrong with the spin statistics theorem there? Can you tell us?
It's not that the spin statistics theorem go wrong, because in 2 dimensions, the spin, what you would call the spin, is only something which is pointing out in the 3rd direction, right? Within the 2D plane, there is no spin.
True.
So, I mean, you just like when you have any statistics, you can have any spin. And so spin statistics theorem is still satisfied.
Yeah, but then that also gets connected with CPT. What happens to time reversal then?
Okay, in I mean, those kind of theorems don't work in this 2D thing, but in realistic systems where you're getting these anyons, it's like you're having some kind of a magnetic field, right? There's a statistical magnetic field. So in that sense, time reverse symmetry is broken, right? T is also broken because.
So what are the equivalents of antiparticles here? So anion, anti-anion, could you say
we
that?
have anti-anions with charge and spin reversed. I mean, it's statistics reversed. E raised to I theta will have an e raised to minus I theta. Non-abelian, the Majoranas, they are found in places where you have superconductivity. So they are their own antiparticles. Majoranas are their own antiparticles. Gamma is equal to gamma dagger. They are real particles.
And when you say that you have non-abelian anions, is this some Lie group or is it a braid group that you are talking?
It's I mean, they're representations of the braid group. It's a non-abelian representation of the braid group.
Okay, thank you.
Yeah.
Any more questions?
Yeah, so I had so Sumati, this I mean, this Microsoft experiments, I mean, like, is it in a condensed matter system or it's some artificial quantum system? And can
It's
you also
condensed
say
matter people. It's condensed matter people, and they have been. I think the experiment has been going on for some time, and the paper came out in 2022 actually, and was published in 2024.
Okay,
So it's a condensed matter. Chetan Nayak and.
So it's similar to the earlier setup of this, like,
Huh?
it's similar to the earlier setups, or it's completely different, like the earlier ones where you had nano.
It's the same kind of thing. What they have now done is that they can also, they measure both at the left side and the right side.
Okay.
They did not, in the earlier experiments, things were being measured at one end and not at the other end.
Okay.
So then I think Das Sharma and company came out with a set of protocols saying all of this has to be satisfied for it to be called a Majorana. Okay. And they can also show the gap closing and opening again. So they can tune through the topological transition. They can start with a system with no Majorana, then change the parameters of the system, and then go see the Majorana. So that has been actually done in about half of their samples, they got it. And then they have done detailed numerical simulations, and they match it, and they believe that they've seen it.
Yes, please.
So when we are saying that marijuana particles are their own antiparticles, what particular properties are we talking about?
Gamma. I mean, I wrote the fermions. Any fermion can be written in terms of two real. Fermion operators are complex, right? You can write a fermion operator, say something like a C dagger, a psi dagger operator, right? You're familiar with that, what I'm saying?
I'm not.
No, fermion operators are usually complex because antiparticles are different. So if you take a fermion operator and you take its conjugate, right? You Hermitian conjugate or something, it'll give rise to the other. You can write this C psi dagger kind of a thing, which is a charge conjugation acting on
that's
that, right?
charge.
So that will give it's a complex operator.
Okay.
So what happens is that just like any complex number can be written as a plus IB,
Yes, yes.
here you're writing a complex fermion operator as gamma 1 plus I gamma 2, and the gamma 1s themselves are real.
Okay.
And those are what I'm calling the Majorana operators.
Okay. Okay. But I need to okay, thank you.
If there are no more questions, so we'll thank Samati again. Thank you very much for the question. So we will have a tea break now. It's for 20 minutes, and we'll meet again at
4:15.
4:15.
4:15.
4:15.